This is problem 17 in chapter 9, where a 6-meter ladder is resting against a wall. In the book it actually talks about a rain gutter, but we'll use it in the wall. We're trying to find all the forces that are acting on the ladder. So first of all, it's a 6-meter ladder, and there's a person on it, so the weight is acting at a location 3 meters from the bottom. We also have the center of gravity of the ladder itself, which is acting 2 meters from the bottom. We're not sure why that's not in the middle of the ladder, but there you go. We're not given the angle, but we can find the angle from taking the cosine of 2 meters over 6 meters. So that turns out to be 70.5 degrees. So let's look at the forces that are acting on the ladder. Obviously we've got the weight going down and the weight of the ladder going down. We have a normal force coming up, and that's going to hold the ladder up. We also have a normal force from the wall. I'll call that N prime, pointing perpendicular to the wall. In the book it represented this that it was resting on a rain gutter, so it would be connected to a point, and in that situation the force came out from the rain gutter perpendicular to the ladder. But in this case we're going to interpret this as a normal force against the wall. And then lastly, to keep the ladder from slipping, we have a frictional force there. The person weighs 70 kilograms, so that's 686 newtons. The ladder is 10 kilograms, so that's 98 newtons. So there's 3 conditions for equilibrium: that the sum of the forces in the x and y direction are 0, and the sum of the torques are 0 as well. So let's look at the forces in the x direction. We know that equals 0 because the ladder is standing still. In the x direction I have n prime in the positive direction minus f, the friction. In the negative direction that equals 0, so n prime equals f. Don't know what the numbers are, but we know they're equal. In the y direction, we know that equals 0. In the positive direction I have n, in the negative direction I have minus the weight of the person minus the weight of the ladder equals 0. So n equals the weight of the person plus the weight of the ladder. We know that n equals 784 newtons. The third condition of equilibrium is that the net torque is equal to 0. So the first thing we have to do is select an axis of rotation around which we'll analyze the torque. It can be anywhere on the ladder, that's fine, but if we pick it where there's forces applied, then those forces go away, because torque is force times the perpendicular force to the ladder times the location of that force from the pivot point. So if we select our pivot point here, both friction and the normal force go away because they have an effective R of 0 and they don't turn the ladder at all. That means we just have 3 torques to worry about. So how does the left side of this equation look? First of all, we have the normal force at the top acting at 6 meters, and we need to find its perpendicular component. On its own, that would create a clockwise torque, which we usually call a negative torque. The second torque we see is a positive torque of the weight of the person acting at 3 meters. And again, it's the perpendicular component of that weight. That's counterclockwise, which we call a positive torque. Same thing for the weight of the ladder. That's acting at 2 meters. And we know that that sums to 0. So from a physics standpoint, we're done. We've used Newton's laws to analyze this situation. We've created 3 equations. We can certainly find what's going on. The difficulty in this problem is understanding more about what the perpendicular signs mean in these equations for torque. And I forgot to put one there. So let's look at it a little more carefully here. If I have a ladder like this and a force like that, we want to find the, in fact I'll make it bigger here, we want to find the perpendicular component of that force, which is a component that's perpendicular, and there's also a component that's parallel. I'm sorry, these should be n primes. And in doing that, we need to apply the right trigonometry to this equation. And that's really the only difficulty of this problem. So if this angle is 70.5, then from geometry know that this angle is 70.5. We know that this is 90 minus that, so this is 29.5. And we know that this is a right angle, and so that must mean this is 70.5. Okay. So from the point of view of this angle here, the perpendicular component is an opposite. Therefore, I can conclude that n prime perpendicular equals n prime times the sine of 70.5. Hopefully that makes sense. Let's look at the other forces, which are the weights coming down. I'll just look at one, and we'll conclude that the other is similar. We're looking for this component, weight perpendicular, and here's our triangle. We know down here that this is 70.5. If I think of this as a right triangle and this being 90, then this is 29.5, and this is 70.5. So therefore, W perpendicular equals the weight times the cosine of 70.5. Okay. So taking these findings back to our equation here, I've got minus n times the sine 70.5 times 6 meters plus W times the cosine 70.5 times 3 meters plus WL cosine 70.5 times 2 meters. Okay. So in this equation, I know everything but n prime. I know the sine of 70.5, I know the 6 meters, I know W cosine 3 meters, WL cosine 2 meters. So I can solve this to find n prime. And it turns out that n prime equals 131 newtons. So, going back to our original problem, what are the forces? I have a normal force coming out of the wall of 131 newtons. Because that's equal to the friction, I have a friction holding the ladder from sliding that's also equal to 131 newtons. And then I have a normal force from the floor of 784 newtons.